Welcome back to Elements of Chemistry. Today we're going to talk about average atomic mass. Atomic mass is different from mass number. If you recall, mass number is the number of protons plus the number of neutrons, and it's always a whole number. But on the periodic table, the numbers aren't always a whole number. So what's going on here? Well, the periodic table uses average atomic mass. This takes into account all of the known isotopes. Remember, these are atoms of the same element with different numbers of neutrons. So all of the known isotopes and their relative abundance in nature. So this is why those numbers on the periodic table change every few years. We find more elements as we explore planets in our solar system, as we look at in stars, we see element compositions change. We find more deposits of things. So things do change. The periodic table is growing. We're adding more elements all the time, and everything's approved of or agreed upon internationally. Okay. So if we look at the periodic table, we see that boron has an atomic mass of 10.81. There's no single atom of boron that has a mass of 10.81. You're either going to have the isotope boron 10 or the isotope boron 11. Boron 11 tends to be more abundant in nature. It actually has a natural abundance of 89.1%. So the average atomic mass is going to be closer to 11 than it is to 10. We can look at the periodic table and look at elements. Like if we look at silicon, silicon has a atomic mass of about 28.09. That means that silicon with a mass of 28 is by far the most abundant. So the number is closest to the mass of the isotope that we have the most of. Okay, so if boron is 89.1% boron 11, that leaves 19.9% to be boron 10. And we're going to calculate this as a weighted average. A weighted average takes into account the percentages. You take your percent and divide it by 100. That just turns your percent back to a decimal. You're going to multiply it by the mass number, that whole number. And you're going to do that for every isotope. Since boron has two isotopes, boron 11 and boron 10, we would take 89.1% divided by 100 times 11 plus 19.9% divided by 100 times 10. We add those two values up and we get 10.81 AMU for atomic mass units. Copper tends to exist as two naturally occurring isotopes on Earth, copper 63 and copper 65. Copper 63 is 69.15% abundant, copper 65, 30.85. So we can make a pre-guess here and say, you know what? This mass, this average atomic mass, has got to be closer to 63 than 65. But is it going to be above 63 or below 63? Well, since there's no isotopes below 63, we know that this average is going to have to be above 63, but below 65. So let's go ahead and solve this one with our calculator. We're going to take 69.15 and divide it by 100. And then we're going to multiply by 63, the mass of the isotope, and we get a number. That number happened to be, and I'm just going to write it down, but I'll leave it in my calculator. And I keep all the digits here. And then I'm going to take 30.85 divided by 100 times 65, and I'm going to get a number here. I'm going to add those two numbers up. Now, depending on your calculator, this might be easier to do by parentheses. Mine, I can just capture my previous number. And that's going to give me an average mass of 63.617. Now, does that match our check? We said it was going to be above 63 and below 65. So chances are we did this one right. And this is the average atomic mass, so we're going to call it AMU. I'm going to box it because I want that answer to be known. Notice I did not do sig figs here. I want to use all those digits. Sometimes you're going to be given an exact mass, or what we call a unified atomic mass, and it's given the symbol U, not AMU, which is mass of the atom when compared to carbon 12. We arbitrarily gave an exact mass of 12 to the carbon 12 isotope. If that number is given to you, if you're getting something in a U instead of an AMU, you're going to get a more exact answer if you do the U's. But it's done the exact same way. We take the percent divided by 100 times the mass of the isotope, the percent abundance divided by 100 times the mass of the isotope, and we add them up to get our U answer. So this is your turn. Let's go ahead and do one. We've got 3 isotopes of oxygen, oxygen 16, 17, and 18. Oxygen 16 is 99.757% abundance. So we know our mass is going to be really close to 16. But is it going to be above or below 16? Well, the other isotopes are above 16. So our guess is above 16, but not much. The other thing I want to tell you about this problem before you actually do the math. Yes, I know it's really easy when you divide by 100 to just move the decimal place over 2, but when you start getting to numbers like this one, it's really easy to mess up those decimal points. So it's better to just do the math. So go ahead, stop the video for a moment, do this problem, and then we're going to try back and check our work. Okay, hopefully you're back. Let's go ahead and set up our math. We're going to have 99.757 divided by 100 times the mass of the isotope, 16, plus 0.038 divided by 100 times 17, plus 0.0205 divided by 100, those are our percents, times 18. And let's just take it a step at a time. This answer here is going to be 15.96112 plus this one here is going to be 0.00646 plus, oops, I wrote this one down wrong. Did anybody catch that? That 0 shouldn't have been there. Always go back and double check your numbers. It's really easy to stick in an extra 0, and I tend to do that. So we got to be careful with that. You will find what your mistakes are and learn to check for them. Okay, then we're just going to add up, oh, we'll put this one down, all of those numbers. And I'm just going back and capturing my numbers here on my calculator, adding them up, and I get 16.00448. Carrying out all of those digits just to make sure. Okay, let's try one with the unified atomic mass. So here we're dealing with uranium, uranium-234, 235, and 238. Go ahead, stop the video, try this problem, and check your work. Okay, we're back. Remember, we're going to take the percent abundance. Now we're going to do this a little bit sneakier way when you're given data in a table. Remember, our percents, we're all going to divide by 100, and we're going to multiply them by those values. So 0.0054 divided by 100 times 234.040945. And I'm carrying all the digits my calculator shows. You might be hearing a little thunder in the background in your video. It's kind of rainy right now. Oops. 99.2742 divided by 100 times 238.050784. Okay, we didn't make our guess. Well, obviously 238 is the most abundant, so by far. So we're really going to be looking for a value close to 238, but it might be just under 238 or should be just under 238 because the other isotopes are below 238. So we're going to take our values. I'm just screen capturing my numbers here. And I get 238.028906. And remember, this is just the unified unit, so we're just going to put a U, not an AMU. That's a little distinction there. Well, I hope this helped you learn how to do average atomic mass. Remember, stay curious, be kind, stay safe, and I hope you have a wonderful tomorrow. Come back when you need help again. Have a wonderful day.